in which we get to see the sausage made. Or like take a sausage and see what's inside. Wait! Welcome back to the MVPN video series. In this video, we bring Profile 1 section to a close by decoding the packets captured during our videos. That is literally the whole idea and the concept of this channel, so I'm excited. Let's begin. Now, what all are we going to look at in our packet captures? The first thing that we're going to look at are going to be the C-PIM packets. Now, this is the overlay signaling on the SP core. The only difference from Profile 0 is this time we should see these packets LSM switched, or label switched, multicast switched. Anyway, they're going to be in MPLS packets, and we're going to see how we're doing the packet captures at the root, so we will see how the root receives one packet and then replicates it out to whomever it needs to be replicated to. We would see the same thing with C-Multicast packets. The only difference here is going to be that we're going to see the C-Multicast packets on the default tree first, and then on the Data MDT later. So we'll see how the Data MDT is a little bit more constrained than the default MDT. As we saw in Profile 1, we would also see the Data MDT advertisement. Now this is when the PE is about to switch to a Data MDT from the default MDT because the threshold was over or whatever decision it took. But we would see how that UDP advertisement goes out, and it tells its peers all of the relevant information they need to join that new P2MP LSP. Finally, we will look at the MLDP packets. Now, this is coming as a last thing here because usually and normally MLDP is based on LDP, which is based on TCP. So there's not a lot of signaling that goes on other than just the hellos and the acknowledgements. So what we had to do for this is we literally had to reset. So like shut down a link and bring it back up so we could re-signal the MP2MP LSP. And then the P2MP LSP was triggered in response to that Data MDT advertisement. And that's going to be all. So let's get into these packets. So the very first thing we're going to look at are those the C-PIM packets that are switched using LSM. So these are in MPLS frames, and the signaling was already done by MLDP. So let's look at this very first one. Now this is on VLAN 13. So that's the VLAN that is connected between R1 and R3. So let's go ahead and mark that on here. So this would be this VLAN right here. So this packet comes in this way. And if you look at it, this packet is a PIM packet. So this is just a bootstrap router packet, a BSR packet. And this is 224.0.0.13, which is the PIM well-known linked local multicast IP. And this is coming from 1111. Now this comes in on VLAN 13, but if you look at the next two packets, so this packet here 34 and this packet here 35, so it gets multicasted out or label switch multicasted out on VLAN 34. So that is going to be towards R4, so VLAN 34 this way, and also on VLAN 35, so VLAN 35 going this way. So as you can see, a packet comes in, two copies go out, the multicast is really working. Now for all of these all three of them are multicast packets. So the first one is a multicast packet with a label of 27. The second one is a multicast packet with a label of 32. And the one going towards R5 or VLAN 35 is multicast packet 28. So all of this signaling has already been performed by MLDP, and we discussed all of that in our MLDP videos and also in the Profile 1 videos. Now something similar will happen when something comes in. So in this case, the next packet is coming from 4444, and this is coming on VLAN 34, and this is coming in this way from R4. So again, remember the loop prevention has already been accomplished by the way the forwarding states were created inside the root, which was R3. So a packet from 4444 comes in on VLAN 34, and it is going to be multicasted out on, if you look at the next two packets, this is VLAN 13 and VLAN 35. So it is going towards R1, VLAN 13, and VLAN 35, which is R5. So it's never sent back or looped back towards the direction it came from. And just for completeness sake, there is a packet that's coming from XR1, and this is from XR1 via R5. So 21, 21, 21, 21, but this is coming in on VLAN 35. And in this case, so this comes in this way. And where does it go out? It goes out on, if you look at the next two packets, it's VLAN 13 and VLAN 34. So it goes out this way. And then it goes out this way. So we can see how the packets are basically encapsulated inside MPLS. And they are doing the same thing they would do with GRE. Now the next packet we're going to look at, so I'm not going to look at the actual structure of the PIM packets, because C-PIM, that's basically just enterprise PIM that is now encapsulated in Multicast. So look at any PIM videos and you would get that information. Now, the next thing is the C-Multicast. So we're done with C-PIM. Those were the first 9 packets. The next 3 packets are all C-Multicast packets. So in this case, the source is up here. The sources are 10 right up here. And our 10 multicasts a packet to 239.123. That packet goes to XR2, and XR2 is going to send it to R4. Now this packet capture once again was done from the perspective of R3, the root. So the root is receiving this now on VLAN 34. So if you look at the highlighted packet here, this is VLAN 34. So it comes in on VLAN 34 this way. And because it is, so right now there are no data MDTs signaled here. So this is all default MDT. So the C-Multicast packet is going to take the same path that the C-PIM packet took. So basically it comes in on VLAN 34 and it is going to go out on VLAN 13 and also on VLAN 35. So out this way on VLAN 13 and out towards R5 on VLAN 35. So in our particular case, if you remember, the receiver was all the way down here, R9. So what R1 is probably going to do to this packet is probably just going to drop it. And that's why we had the Data MDT, which is the next packets here. So once R4 realizes that the rate of the packet is, or the rate of the packets are high enough, and we were sending these pings, they were number 1 big. So remember, they were 1,000 bytes. And they were also pretty frequent. We were sending, I think it was either a ping bomb or we were sending one every second, something like that. So it's something to exceed that 1 kbps data rate. So 4444 or R4 then essentially triggers the switch over to the Data MDT. And this is on a well-known port. This is a UDP packet. And this is multicasted out on the same address as PIM, so 224.00.13, and this has to go out on the default MDT. The reason for that is that this packet now has to reach all of the PEs that might have not signaled their intent before. So you don't know, as 4444, you have no idea which PEs are interested on it. But if you send this packet out with the right mapping, then the PEs can just join the tree that you want to join, that you're intending to signal there. Now, I haven't decoded this particular bit here, but essentially what this is signaling is it's signaling, and you can see some bits down here. You can see 4444. So 4444 would be the PE, or the, if you think about in terms of PPIM, this would be the P source, but 4444 is intending to signal this. And later on, when we look at the actual signaling for MLDP, you would realize that this next part here, all of this 000E, 02, then B, and 0101, all of that is just the opaque value that is being signaled. So it is based off of the VPN ID. In this case, this is 100, So 100 and then 100 and 0001. So 100, 100, 1 was the VPN ID that was chosen, or it was based off of the VPN ID with a suffix of 1. So that is now that's the opaque value that goes out in this Data MDT advertisement. And someplace here you would also have the source, the C source. Now remember, the C source here is 10, 10, 10, 10. So if you convert it to hex, it goes to A. And then you had 239, 1, 2, 3. So this is that 239. So EF is 239 in hex, then 1, 2, and 3. So all of the values, so the mapping for CSCG, that's contained in this packet. The root, which is 4444, is contained in this packet. And then finally, the opaque value, the whole long 14-byte opaque value, is also contained in this. So essentially, this packet goes out on the default MDT. This is going on VLAN 34. So this way on VLAN 34, that's this packet. And then again, it's going to be replicated out to the other two VLANs, which is VLAN 13. So R1 is going to receive a copy, and R5 is going to receive a copy, which then it should forward to XR1. So once that happens, and this next thing is not apparent because I have put the P2MP signaling a little bit towards the end. So what's going to happen is then that P2MP signaling is going to come in first. So 1 second, let's look at the P2MP signaling. And then we will look at how the switch over actually takes place. So for the P2MP signaling, I have that towards the end a little bit, which is going to be right here. So this is the P2MP signaling that R5 is sending over to R4. So remember, the P2MP signaling is going to be a little bit different. This is going to come this way from XR1 because XR1 is the only one who is going to signal adjoined to that P2MP tree because that was the only PE that had an actual receiver behind it. And then R5 will take the shortest path over to R4. And remember, once again, this interface here in our topology was shut down. So there was nothing on this interface. Or this interface was shut down, so there was no signaling that could have been done there. So right here, and that's how, because that interface is shut down, then the shortest path from XR1 to R4 is via R5. So that's why you see this particular message for P2MP signaling, you see this on VLAN 45 and not on VLAN 421, which would have been the normal case. So this is a label mapping message. Now, this particular message is not going to signal which group or which CSCG you want to join because that signaling was already done up here. So you're just basically responding MLDP wise to this message up here. And all you are saying is, let's break this down. So this is a label mapping message. The FEC is what we are interested in. And finally, in the FEC elements, we see that it is a point-to-multipoint FEC. So it's not a multipoint-to-multipoint FEC. It is a simple point-to-multipoint FEC. And what do we need after the point-to-multipoint FEC? We need the root address, which is right here. So the root of this particular P2MP is going to be the PE that signaled it, which is 4444. That's the PE that's going to dump all of the multicast data on here. So 4444 being that. Then you have the opaque length, which is, it's a TLV. So essentially it decides how long this value is going to be. And then this value itself can be broken down into basically MDT value. So in this case, this value is going to be, let's take a look at this here. So that value is going to be, you'll have to break it down. So basically what I did was I took this opaque value down here and I brought it up and I tried to break it down. So 02000B, that essentially just seems to be the code that they're using for MDT. So that particular sequence there tells the other router that to decipher the rest of this value as an MDT value, or basically break it down into the VPN ID and the instance number. So the next 3 bits, or the next 3 bytes, are going to be the first part of the VPN ID. So remember, the VPN ID was something colon something. Well, that's something colon something that I may not have mentioned in the lecture. It's all in hex. So it's a hex value, a 3-byte hex value, colon, followed by another 4-byte hex value. I don't know how they came up with this, but it basically breaks down into the OUI and then the VPN. So in this case, the OUI was 100 and conveniently the VPN was 100. So the first 3 bytes in hex are 100 as the VPN value, or the OUI value. And the next 4 bytes, the bottom portion of it, is also 100 because it is 100 colon 100, which you can see here. Finally, the instance. Now the instance 0 always belongs to default MDT, so that cannot be used. So in our case, we just used the next sequence, which was the Data MDT, or which was one which we used for Data MDT. So that's how you break that value down, but essentially it's just signaling an opaque value. So once that is done, the next part is just the label. So in this case, the label was 1C, which I'm not that good at hex, but whatever 1C was the label. Let's quickly do this. So 1C is going to be C. Looks like that's the value 28. So what should happen is now 239.123 should start using the label value 28 as it goes from R4 to R5. So number 1, I want to see if I captured the right interface here. So here's the MDT as it goes out. So sometime after this switching would have taken place. And then you should get this value, which, yeah, you can see this is label 28. This is also on 34, so no, that's not the right label. This switches on to 45 with the label 21. And I know what the problem is here. So basically, I think when I initially captured these packets, I forgot. I'm trying to see if that is the case. 45 and 45. Yeah, those values don't match there because I think basically I re-triggered this at some point later and captured these packets earlier. So basically what you have to see is whatever value you see in here, if it's in the same instance, then this label value should be reflected in the value you switch over to when you switch to the Data MDT. So in this case, we're expecting 28. But what I can tell you is when the P2MP signaling was done for this particular Data MDT, so for 10.10.10.10 to switch to 239.123, the value of the label that would have gone out in the P2MP signaling would have been 21. So that's why you are using value 21 and you keep using value 21. And essentially what's happened now is that those packets that were on the default MDT here, so they were going from R4 to R3, are now going directly from R4 to R5 and following that light blue path over onto XR1. We see this one more time, so let me see if I capture the right packets here, because I have 229.124. Is that the right packet again? That again may not be the right packet, so I'm trying to see if this is. Yep, this is 239.124. So once again, I don't have the default MDT packets for 239.124, not at least before the capture. So here's the default MDT packet for that second group, the CSCG, 239.124. And there should have been a packet before this MDT signaling, because that packet would have triggered this MDT advertisement. It's the same advertisement as that light blue path. So this would have gone out to R1 and XR1, and they both then would have triggered, or I'm sorry, R1 wouldn't have triggered, XR1 would have triggered. So the reaction to this, getting multicasted out to 13 and also to 35, is this packet down here. So this is another P2MP packet, and we can break it down the same way. So this is 100, right here 100. Then the VPN ID is, so OUI is 100, the VPN is also 100, but the instance number now is 2. So this is basically joining that second FEC, or it's signaling the intent for that 239.124 group. Now the label here is 1B, which would be what? It should be 27, right? So 1B would be 27 because 1C, 1B. Let's make sure. So it's label number 27. Let's see which label we actually captured. And this time the label is 29. So again, guys, the problem here is I captured this P2MP packets a little bit later for a separate signaling, and I captured the Data MDT packets in a separate part of the capture. So basically what should happen, ideally, if you're capturing in sequence, is the label that you see signaled in the P2MP here, so in this case it was 1B, is the same label you should see the Data MDT packets in. So my apologies here, I didn't capture the right packets. The last thing then that is left is the basic MP2MP signaling. Now this is the default MDT signaling. So let's clear out our board a little bit for this MP2MP signaling. And these are these two packets. So in MP2MP, you have to realize that MP2MP signaling is going to have two FECs. So there's going to be a downstream FEC that is signaled from a downstream device. Now, in this case, that device happens to be R5, and it is signaling to the root. So it is signaling on behalf of XR1. We know this because of our topology. So R5 is signaling to R3. And this is the, no, not that. This is going to be the downstream signaling, or the downstream FEC, because this is the packet that you want to receive the data on. So let's look at the contents of it. So once again, now with the P2MP FEC, which was right here, you see that the Wireshark is pretty good at actually recognizing what type of FEC it is. With the MP2MP FEC, for some reason, it's an unknown FEC type. So what you would have to do if you were really interested is look at the FEC elements, look at this whole thing, and then you have to break it down sort of like how I did. So in this case, the breakdown is right here. In this case, let's see, the downstream FEC. So in the downstream FEC, the one that is being signaled from R5 to R3, basically what I've done is I've taken this entire value and I have broken it down up here. So it's a downstream FEC, which is 08. It's address family IPv4 from 0001. The address length, because it's IPv4, is 4 octets. And then in the address, you would have the root node. So for the root node for MP2MP, it's going to be somewhere, something central, hopefully. In this case, it was 3333. Then you're going to have an opaque length. Now, the opaque length in the packet capture is exactly 14 octets. When you look at it on iOS, for some reason, they decipher it as 11 octets. So they're missing 3, or they're deciphering 3 somehow differently. But I'm not 100% sure why that is happening. So the 14 octets, when you break it down into the opaque value, once again, the 02000B. So if I look down here, 02000B, all of that basically means MDT. So decipher the rest of that value as a OUI, VPN, and sequence number. So the OUI is 3 bytes. The next 3 bytes are the OUI, so 000100, that's the OUI. Next 4 bytes are the VPN ID, which is, or that's how they break it. That's how they break the VPN ID down into the OUI portion and the VPN portion. So we just call it the VPN portion, which would again be 100. This is again programmed in hex. So when you're entering it on the CLI, you're actually entering it in hex. Very important to remember. And then finally, the instance number is going to be all zeros, because guess what? This is default MDT. So the only thing to remember here is 08 is just a downstream FEC. Now, once again, that FEC has a label associated with it. In this case, this is 1D. So once he was 28, this should be 29, right? Hopefully. So that's the label that 3333 or 5555 expects to receive the data on. Now, in response to this, 3333 should be signaling an upstream LSP. So what should happen here is this part should be the upstream LSP. And this is where, this is basically the label where 3333 expects the upstream data coming from XR1 via R5. So once again, this basically generates an unknown FEC type. So once again, I've taken all of this data and put it up here. And one thing, so I will share this capture file out with you. If you look at both of these packets, so packets number 24 and 25, the MP2MP FEC packets, they both have packet comments associated with it. And in the packet comments is where I have included all of this information. So if you want to see, this information is available in the packet comments. So just look at the packet comments and you would see the same information there. And I'll try to include the text file there as part of the packet capture as well. But the only difference, literally the only difference here between the upstream and the downstream FEC, so down here, is this 07. Because 07 is an upstream FEC type, whereas 08 was a downstream FEC type. Once again, there's the address family, the address length, and the actual address, which is 3333. The opaque length, which is 14 octets, deciphered as 11 octets in iOS for some reason. Once again, this is MDT. The OUI is 100. The VPN is also 100, so 100:100. And the instance, as we know by now for default MDT, is going to be 0. Finally, there is a label that is going to be associated with this FEC. This label was 18. Once again, I'm going to use my calculator here to cheat. I'm doing it off screen. And this is 24. So that was label number 24. And the further packets between R3 and R5, going from R5 to R3 actually, are going to be in label number 24. But believe it or not, that is all when it comes to the packet captures of this. So, yeah, I'm going to include all of this information in the description box below, and you can download the packet capture and go through it at your own leisurely pace. So up next, we will further optimize our SP core. So that's all we are doing, right? So we'll keep optimizing and optimizing and optimizing till we get something that we like. So we'll further optimize the MPLS core, and this time we will eliminate the need for C-PIM. So far we have overlaid C-PIM on our SP core. Moving on, we would try to just completely get rid of C-PIM when it comes to signaling across the SP core. Now, there are multiple ways of achieving that signaling. So signaling still needs to happen, but we just don't want to use C-PIM for it because it's a soft state protocol, and basically we just want to get rid of that extra state all the time. So there are multiple ways of achieving this, and you can use MPBGP or you can use mLDP itself to perform the signaling. That opaque value makes it very flexible, and you can just use mLDP to perform the signaling. And most of these technologies, you would think of them as the next generation. So this is the next generation MVPN. So we'll cover all of that. But till then, I would like to thank you for joining us, and I would urge you to stay tuned for our next video. Thanks.